Hello, everyone. Welcome to the COP28 Blue Zone. I'm TCP Secretary General, Dr. Qiming Peng, and I'm the moderator today. And I would like to introduce a very good idea. It's NCKU, National Cheng Kung University, their progress about the carbon neutralities. And another professor online is Chen Ziyong. He's a team leader. Hello, Ziyong. Hello. Hello, Professor. Nice to meet you. And actually, I'm in Dubai in the Blue Zone. And Professor Chen also will be joining us later on. So today, we will talk about the progress of the NCKU, what they did about the carbon neutralities. Actually, you know, the fossil fuel in this COP is a very important topic. For example, we want to phase out or phase down the fossil fuel. However, in our daily life, we still need the fossil fuel or our clothes. We do not have any kind of clothes. And the statement by the United Nations Secretary General Antonio, I remember before the COP28, he mentioned about the solution is well known and the leader must act to limit global warming to 1.5 degrees and the end of the fossil fuels. And however, the impact of ending the fossil fuel have some problem. For example, this session will affect the human needs, including our clothes and our electronic products, medical products, and vehicle parts, all of which require the fossil material like oil, natural gas, and the coal for steel making process. Global carbon capture initiate actually currently carbon dioxide from the factory chimney and the atmosphere is being captured to obtain carbon resources on the Earth's surface stored in the solid and liquid chemicals known as CCUS. IEA reports recently, there were lots of reports in this year, and they mentioned CCUS is one of the key technologies for achieving global net zero emissions, laying the foundation of long-term energy and chemical goal. And before that, the NCKU, National Cheng Kung University, CCUS demonstration plant, actually it starts from the end of the year 2021. And the National Cheng Kung University in Taiwan built the first CCUS demonstration plant, and then marking an important step toward ending the fossil fuel era. So the president, we will give an introduction from the president of the NCKU, President Shen, and we have a pre-recording video, please.
Dear Secretary General Peng, Professor Chen and his team, Vice President Li of the ITRI, all the distinguished delegates all over the world, the corporate representative, as well as the scholars and the students join us online. Nice to have you here. I am the president of the National Cheng Kung University in Taiwan. It's my great honor to speak to you through this pre-recorded message. We feel truly honored and excited today to be invited by the Taiwan Climate Partnership to introduce our university innovative work in zero carbon energy technology right here at the United Nations Climate Summit. A key concern of this COP28 is a global collective effort to achieve carbon reduction, particularly in the transition to zero carbon energy and the replacement of fossil fuel. We are proud to announce that Professor Chen's team already established Taiwan's first carbon negative demonstration plan at the end of 2021. This groundbreaking technology of artificial synthesized green natural gas, e-methane, has successfully completed its trial phase, making an important step toward commercialization. E-methane is exactly the kind of key zero carbon energy source for the 2050 green energy strategy of Europe, Japan, and other countries. We feel honored to present our scientific work at the stage of the United Nations and to contribute globally in combating the climate change. Finally, I would like to extend my gratitude to all the distinguished participants who honor us with your presence. I hope this forum will not only showcase Taiwan's new achievement in CCUS technology, foster future international collaboration, but also inspire young people to engage in this crucial campaign against the climate change. Facing the urgent climate crisis, we need the strength of the younger generation more than ever. Taiwan will go on with you. Thank you very much.
Yeah, thank you, President Shen. And I think he is the first one in COP28, the university president in Taiwan. I think it's very wonderful, and the video is quite very good. And beside that, we have two speakers here in COP28 Blue Zone. The first one is Professor Wang Zhenjie. Professor Wang, actually say hello to everyone. And he is Dean of the Engineering College of the Southern Taiwan University of Science and Technology. And he is a professor of Department Chemical and Material Engineering. And actually, you are team leader under the Dr. Chen, right? Zhiyong Chen. And beside that, we also the Doris Dennis. Yeah, and she is a very important expert about the carbon credit operations partners. And actually, I know her in Paris agreement. What number? COP19 in Poland, Warsaw, or earlier. Yeah. And she is an expert about the carbon, lots of carbon issues. So later on, they will have some presentation. And about the president mentioned about because the fossil fuel, they want to phase out the fossil fuel. And however, it's not so easy. Just I know the president Shen mentioned about the NCK use e-methane technology, but e-methane, actually, I don't know what is e-methane. Probably Dr. Wang can introduce this for me, because the e-methane is a kind of the alliance of international standard as a carbon neutral fuels, and such since its combustion offset the capture CO2. So probably lots of people don't understand what's the process. And however, you can explain to us. It's also a key energy source in the EU and the Japan 2050 national green energy strategies. So what you propose is not only for Taiwan, but for meet the EU goal and the Japan goal. And I'm wondering to the Dean Wang and about the current development of e-methane internationally and the role in the future without fossil fuel. Please, Dr. Wang, please.
Thank you, Professor Peng. It's my pleasure to introduce CCUS technology, the development from National Cheng Kung University. I'm Zhenchen Wang. I'm also happy I'm the member of this research team. E-methane, if you know the shale gas in USA, the e-methane is the compound of the shale gas. Okay, so it is the raw material in the chemical industry. Is very important. We will know the fossil fuel day end is proposed from the last year, COP27. And the EU agreed to push this fossil fuel phase out in this time. So we must face this problem. We will know oil and gas is come from the fossil fuel, and how they improve our daily life. It can make the cosmetic, this woman very like is to use that. Food and packaging, construction, plastic, agriculture, medical, and entertainment. iPhone also need oil and gas to make this product. So it is around our daily life. So when if oil disappear tomorrow, it will be happen. Oil is the energy intensive and versatile liquid, which human has been exposed on a large scale since 1850s. After 107 years, many are calling for a product to cease completely. The question is, what will then happen? In the winter, can you call Siri? How do you light a fire, Siri? And when you have planned to take a tree, you must be taken off by your leg. is if you think it's wonderful, you can give us the fast sale. So China client able say that's our fast sale unrealistic because it's very important. So if we do not use the crude oil, and we must think where do upstream raw material came from? Is carbon dioxide possible? Yes, it is possible. It's a primary solution. Since 1988, scientists have developed some technology to convert carbon dioxide into methane, fuel, and some green chemistry. So this technology we can call power to gas or power to X. X is everything, including hydrogen, methane, or fuel. For example, this is audio car company. They have built the 100 million ton of e-gas per year in Germany, and this finding around 2,008 meter ton of carbon dioxide. And their e-gas have supporting the world first carbon neutral container ship successful sail in this year. So this is a very popular issue in the world, such as in Asia, Japan. Japan company, they plan to city gas consumption of the gas field should be contained in methane approach to 90% in 2015. European Commission also plan to manufacture some e-methane in 2015. So this is a big feature in now. And we must face some challenge or power to gas or power to X. The first important is high performance catalyst, because if we can react at a low reaction temperature, it means your energy consumption and your cost will be decreased. The second question is hydrogen from green power. We will know that green power is not enough now. So you want to use the hydrogen, you must search in the other source. Maybe biogas from dry methane reforming is one of the methods. The final problem is we also need excellent engineering to design a high efficient process. Maybe some advanced should be developed in the future. Thanks.
Yeah, thank you, Professor. Actually, lots of audience come here because if we want to phase out the fossil fuel, you know, our clothes, everything, we are from Taiwan, the ICT industry organized together to be a TCP. Actually, it's ICT industry. Lots of material, for example, our iPhone, our iPad is from the fossil fuel. And so they have a new technology called e-methane or e-protein to help to replace the fossil fuel. So it's another new technology. So I will continue to the Dean Wang, and you are expert. Probably you can explain what is e-methane or e-protein, because the global CO2 emission this year reached 41 billions. And to resource such a large amount of CO2, a kind of export capacity was needed. And based on e-methane, your university catalysis can produce the e-methane and e-protein, and the key upstream raw material for the petrochemical industry. I would like to ask you about the potential of the CCUS demonstration plan to replace the traditional subterranean fossil material, please.
Okay, thanks. Just I mentioned the first question we must face is a high performance catalyst, and this is very important.
Can you explain what is the catalyst?
Catalyst is some enzyme, like the enzyme in environment. So catalyst is used in the chemical industry. It is very important things. You can take a short time to take the chemical. You took a short time means is energy saving and the cost will be decreased. And now, NCQ research team, they develop some cutting-edge catalyst. This is very important in chemical industry. It can convert carbon dioxide into e-methane, in ethane, and in propane. We will know C1 to C3 can be applied to e-fuel, just natural gas. And if we convert into ethylene and propylene, we will know it's a raw material in the chemical industry. So we can use this raw material to manufacture some green chemical. This research team also developed some novel solvent to capture carbon dioxide from the fuel cell. More interesting, this cutting-edge catalyst, they can convert bio-waste into hydrogen or some chemical. This cutting-edge catalyst, we will know the bio-waste was digested. We can obtain the biogas. The biogas contains methane and carbon dioxide. If we use our catalyst, it will convert to obtain carbon monoxide and hydrogen. We will know these two gases is synthesis gas in chemical industry. This is very popular in now.
Yeah, please. Keep the microphone, please.
Does this account for like agricultural methane production, or is this like solely focused on industrial methane? Oh, it does.
Yeah,
Okay.
yeah, please. Yeah, yeah.
This is our power plant. Oh, a power plant. Okay. And
Where are you from?
US.
From the US. Oh, okay. Yeah.
Okay.
I think the US needs such as kind of techniques. Yeah.
okay, this research team also developed some high performance bipolar membrane. If you want to take a hydrogen from the water electrolyte, maybe biopolar membrane is a good choice because it will be a high efficiency to obtain the hydrogen gas. And we have 60 patent now. I introduced some cutting-edge catalyst and the process. We can see it can operate at a low temperature and low pressures. In general, we must be manufactured in methane maybe approach to 300 Celsius degree. But in this catalyst, we can operate lower than 180 Celsius degree. And the second, we can convert 100% with a short period of time because of this catalyst. And the third, we can produce a high value ethane and propylene, maybe over than 20%. It's more important because it's like a shear gas. And finally, our process fits all oxidation and other process. Our power plant construct in the NCKU campus. It will be synthesis 8 tons of C1 to C3 per year. And if we...
Yeah. Okay, thank you very much. Thank you.
Thank you.
Friends from
Thank
the
you.
US. Yeah, keep in touch. Enjoy the NCKU. I'm wondering, Professor, the previous page. I think the key issue is the temperature, right?
Yes, yes.
Yeah.
And the other special is ethane and propylene.
Okay.
Okay,
Yeah.
next PPT will show you what is important because we can see the shear gas in the USA. Their ethane content no more than 20%. And if we use our cutting catalyst, we can convert carbon dioxide into high content of ethane and propylene. I just say that over than 20%. More important, the shale gas in USA, they has many impurities such as salts. But if we use carbon dioxide, their product is very pure and no sulfur. It means we will decrease the PM 2.5 particle because it is also the acid rain source. And more interesting, if we use the carbon monoxide, which gas came from steel industrial process gas, the reaction temperature will be lower to 150 Celsius degree. More interesting, their E-ethane and E-propane were over than 30%. This is very valuable So our catalyst is the steel and the petrochemical joint negative carbon material. So maybe next we can search some industrial company which have a technique to convert ethane with carbon dioxide into ethylene and propylene. Ethylene and propylene is a raw material of the chemical industry. They can manufacture some many chemicals. So if this process is going, we can after the approach to net zero chemicals. And about the bipolar membrane, we can see this. The Upton Corporation is a Japanese company. Their bipolar membrane can upturn the hydrogen. Their water slip voltage is 1 point voltage. It's very high efficiency, over than 98%. However, our research team, we employ plasma energy to induce radical in the surface of membrane. Then the polymerization will be happen in the interface. So we can manufacture very thin thickness of the membrane. And when we performance in the water electrolyte, we can see their critical voltage will be down to 1.8. When we operate more slightly high temperature, their critical voltage will more decrease to 1.7. So this is a very good bipolar membrane. Their hydrogen production is high efficiency, and its energy consumption is very low. It's valuable for commercialization. So I think this bipolar membrane is the best choice membrane for water electrolyte from the green energy. Thank you.
Yeah, thank you, Ding Wang, and a very wonderful talk. And I'm not a chemical engineer guy, but I understand what you say. It's not easy from knowledge to the common people they can understand. So right now I will give the floor to Dr. Jian, because from the science or technicals is wonderful. But for the business point of view, because they need the business support, I'm wondering, such as kind of service, did they have any kind of business model, or just only the scientific research? Because I think in the long term, still the ecosystem they need a business model to survive. To sustainability is very important. Is there any connection with a carbon credit in the future, please?
Okay, thanks, Dr. Peng, and thanks, Professor Wang. So next time, okay, we say the technical part has been gone. Okay, so what I'm going to explain to you or to share with you is more business part. So what we're going to do is that, as Professor Wang already mentioned, that so our technology can produce decarbonized gas energy. And what is important that actually we capture the CO2 in the chimney of the industry that will be released to the atmosphere normally as a greenhouse gas. But what we do is capture the CO2, or we say carbon dioxide, from the chimney, then using them as a raw material to produce a synthetic natural gas, which is methane. So it means that all the emissions can be captured and then used as a material to a natural gas to replace as a raw material again in the industry or for the with the household in the future. So our business model is to decarbonize the gas energy, and how we do actually, just give a very quick picture here. So we capture the carbon from the flue gas, which are hard to abate from different sectors. For example, steel mill, aluminum. We say fertilizer, for example, sort of them. And we capture all the CO2s, then we put them together with which the hydrogen has been generated from green sources, from renewable or from the liquid hydrogen from biogas. And with this, we have different type of the patent for the biogas absorption and also with the reactions between CO2 and hydrogens. So we capture the CO2, then put them together with the green hydrogens to produce e-methane or e-ethane or e-propane and which are very important. So methane is what we said is like natural gas, but it's a synthetic. Ethane in propane are actually very important raw materials for the industry. So these are the very valuable sources that we put them back to the industry as raw material or the sources for combustion in the future. So we capture the emissions into natural gas again. And this is very important for all these cycles that we can get the carbon credit actually from the capture of CO2, the carbon emission reduction. But what is important is here is that when we capture the CO2 as a greenhouse gas emission reductions, but we need to take care that all the hydrogen produced, it needs to be less carbon leakage. If we produce the hydrogen with electricity like fossil fuel again, or the other fossil fuel terminations, that would be the problem creating more leakage from there. So important of this one here is that we have to make sure that we capture the CO2, but the hydrogen has to produce from low carbon sources. So this is the key to avoid the carbon leakage. Okay, and next one, I'm going to share with you. So if we want to have a green hydrogen productions, what it happens from the arena, the research is shared with us that we can see that actually there are exporters and importers of hydrogen from different places, not only the green or non-green. So we say the hydrogen, it can be exported. So the yellow part, the yellow dot actually is the importing regions. And the dot with the blue dot actually was exporting. So what we can see is that where are the hydrogen importing countries like in Asia and also in some central of Europe? They are importing hydrogen from the other country or the other sites. And what are the exporters of the hydrogen, or especially the green hydrogen? They are coming from where the renewables are most popular or most easy to get with. For example, like South Africa, like South American, like Middle East and Australia, they have a greater opportunity to producing and exporting a green hydrogen. So these are the important. And what is the shortage for Taiwan? Actually, in Taiwan, we are lack of the land sources. We don't have lots of spaces to produce renewables. So that's why that even though we capture all the CO2s from the chimney, from the flue gases, but we're still facing the problem in the previous one that we cannot have a green hydrogen. So these are the business model we are creating. After that, we are going to use global sources as a base in the future. Okay. So, and just would like to share with you actually what's the problem is that when we are producing the green hydrogen, the most more than 3/4 of the electricity is really accounting for all the cost. So important things is really from the, we need to have a renewable source for the green hydrogen production. And instead of going back to this one, we have two different type of gases now, CO2 capture. CO2 can be captured in a really easier way. I mean, around 30 degrees Celsius, it can be liquidized. But hydrogen can only be liquidized. This is more than 200 or minus 270 degrees Celsius. So if you think about technology and then also think about the capability or even the storage safety, then CO2 is much easier to be captured, to be liquidized, to be transported, rather than the difficulties of hydrogen. So when we compare with this one, so we capture, if we want to ship the hydrogen everywhere, our recommendation, it will be shipping CO2 to where the hydrogen, green hydrogen can be produced, which are much easier and more economic. So what we say that at this time here, that actually is a CO2 captured. So to optimize the CCUS value chain on a global basis, so we're shipping CO2 to where the green hydrogen can be produced. And to realize our reactions between CO2 and hydrogen to produce methane. So step one, we capture the CO2 and liquidize it. And then we transport the CO2 to where the green hydrogen to do it. So this is something that, so capture of CO2 from industrial flue gases and shipping from CCUS for CCUS or CCS is really an additional solution contributing to the greenhouse gas reductions. Of course, we would like to have these all the shipping carriers. They are less, we say, greenhouse gas produced one as well. Okay, so what's happening? We can see actually there's a new trend, a rapid growth that many different gas, especially the gas companies in the world, because we would like to first phase out the fossil fuels. It means that the natural gas digging from the ground, it will be phased out soon or in the future. So all the gas companies, they don't have all the natural gases from the ground. What should I do? So they try to get it from the industry. It's really like a circular economic in the future. So what company they are doing actually here, there is a rapid growth of the CO2 shipbuilding recently. We can see, we can observe from the news or, from the media, already happened in Japan, Korea, and German, China, Finland, and Belgium, and Denmark, for example, like that. So people that are, companies that are building CO2 ship carriers to transport CO2 to meet hydrogen rather than to transport hydrogen because it's much more expensive, it's much more risky to do it. So this is what we can see. And also, so to meet our carbon credit with a less expenses and also less risky, and also with a STEM carbon credit created.
Yeah, wonderful. I have a question to Dr. Jen because, such as kind of US DOE hydrogen shot. 2030, it will be $1 per kilograms.
Yeah.
So right now it's very expensive. So if we're going down the time to the hydrogen, the era of hydrogen will come, right? 2030. Yeah. So such as kind of project is very good for the hydrogen power in the future.
You know why the hydrogen shots can be reduced? Because it's more and more renewable energies. The price of the renewable energy are cutting off. That's why that we can produce green hydrogen with less expensive sources. What's the reason?
Yeah. That's very important. I think that it looks have some business model right now, right?
We do have some business model, but we're showing the end.
Yeah. Wonderful. Yeah, wonderful. So I will go back to some technical issues because you mentioned about we will talk about biogas reutilization and also green syngas. What is a syngas? Syngas, right? SYNGS. Because your model is a CO2 resource reutilization into e-methane, right? Ethane, called ethane, and the e-protein. And such is kind of we can say it's a circular economy and have the potential create a new industrial chains and economy model. So it changed our thinking about the CO2. It changed to another way to do. So I'm wondering because Japan, I noticed about Japan, in the Osaka World Expo, they will use the new technology. It's a showcase about the kitchen waste into the synergy natural gas, e-methane, and also another future of trend of the waste resources reutilization. So the Ding Wang, can you more application of biogas and any kind of the technology breakthroughs needed?
Okay, thank you, Professor Peng. The biogas, we can see, we just mentioned hydrogen may be a two resource. One is obtained by water, electrolyte from green power. The other, we may be consider some resource is come from the bio waste. Because the bio waste was digested, we can obtain the synthetic gas. I just say before, the synthetic gas is very popular in the chemical industry. This is very well-known technology. And if we consider the biogas composition, we will find their ethane is approaching to 16% and the carbon dioxide is 40%. So if we obtain this biogas, we can use our cutting agent catalyst to transfer them into synthetic gas. And I must mention this carbon dioxide by biogas is not enough. So you must add some carbon dioxide from the capture system So it will more carbon dioxide will be used in this system. And the synthetic gas, I show you this this PPT in the below. You will see if you use the synthetic gas, you can manufacture methanol, formaldehyde, or polyolefin, such as this chemical product. So this is a very variable process. So we can approach to net zero chemical. But if we use the DMR technology, dry methane reforming by biogas, we must face some challenge. One is methane activation. The challenge two is thermodynamic and kinetics. The third challenge is catalyst development. The more important challenge is cooking, because if the process happen cooking, it means your catalyst will lose its function. So this process will be it's useless. However, when we use our cutting edge, this cooking will not happen. It's very interesting. And we operate this catalyst in our lab. We can see this experiment data. We operate more than 200 hours. Their methane conversion and the carbon conversion will keep in high level. And our product contain hydrogen and carbon monoxide. The ratio is approaching 1.2. It's very stable. So this catalyst is a very stable catalyst and high performance. More important, when we take this catalyst after 100 hours operation time, we can watch this picture. They are up top row coke foam. This is important. Many catalysts will be form coke in the short time. So I think maybe this is a high potential catalyst in net zero DRM process in future. Thank you.
Okay, thank you, Ding Wang, and you make a wonderful introduction about the reutilization into the e-methane. I don't know the CO2 have so many functions. Yeah, actually, it's a very good idea. So I have a question about the CCS because CCS, what we mentioned, is a carbon capture technology. And another issue is like fundraising. So this topic I will talk about this because Taiwan will need about 40 million tons of CCUS by 2050. Actually, it's a government proposal. And however, the CCUS means capturing CO2. I'm wondering, the Ding Wang, and can you introduce the CCS of your demonstration plant, NCKU plant? And is any kind of the technological breakthrough about this one? And I will ask Dr. Jen. Actually, you mentioned you have have some business model there. And however, what I know, beside the business model, you should have some fundraising for the people to. For example, the Japan, they have the Japan JCM credit model. They encourage the enterprise to join. So I'm wondering, do you have any kind of idea about the fundraising and the ecosystem, how to make it, please? Yeah, in one first. Okay, yeah, you first.
Okay, thank you, Professor Peng. NCKU research team, they developed some very interesting absorbent for carbon dioxide capture. If we want to take this process, capture carbon dioxide is the first step. It's very important to reduce carbon dioxide emission. We will know many methods can capture carbon dioxide. However, if to capture fuel cell gas, maybe absorption is more suitable because amount of fuel gas is very large. In typical, monoethane amine is an alkene liquid. It can react with acid gas carbon dioxide. However, we will know the fuel gas contain many impurities such as SOx, NOx, or oxygen. Then When we use this monoethanolamine, we will face 3 problems. The first problem is if you visual cell consent sucks in lower than 200 ppm concentration or some oxygen, there will be degradation of amine adsorbent, maybe up to 30%. This means you must refresh the adsorbent. It means your cost will be increased. And more important, if we have some side reaction exists in this capture system, such as amine can react with carbon dioxide to form nitrogen amine. This is the carcinogen and ecotoxicity. This is the second pollutions. We are not want this second pollution. The third problem is corrosion. They will corrode some instrument or steel. This means you must cost to maintain this process. And our research team, they developed a novel adsorbent for carbon dioxide. It's potassium acetate liquid. It's a high concentration. So far, I know no research team use this adsorbent in the world. If you absorb the carbon dioxide, the original transparent liquid will transfer to turbidity liquid, and finally, we obtain the starry state product. The starry state, we categorize their composition. We will find they have contained alkene solid, is a potassium hydrogen carbonate. The other is dimer, is a ester solid. Both compound is solid, it's like a foreign tablet. When we add water or heating, we will find this 14 tablet will resource. So carbon dioxide will be released. Then we recover this adsorbent. We can recycle. More important, this is salt liquid. So there no exist side reaction. Let me show you some very interesting video. This is the carbon dioxide dissolved from, sorry, it can work. This is a video. Okay. Now it's going. We can see if we inject tiny water, the carbon dioxide will be released very quickly. It's in the room temperature. It means you know the ultra energy to push the carbon dioxide release, and the release rate is very fast.
Professor, can you explain more detail about the movie? Yeah. Why is the carbon? Why is the carbon the red color or something? Where?
Okay.
Okay. Yeah.
Wait a moment.
Yeah. Okay. Yeah.
We can see this is a slurry state.
Oh, okay.
Of adsorbent after carbon dioxide capture.
Yeah.
So
the
inject water, just water.
Yeah.
Yes, their carbon dioxide will be released very quickly.
Oh.
So we can recover this adsorbent.
Okay.
And we cannot use many energy.
Okay.
So this is very interesting in the academic.
So this is your breakthrough point.
Maybe. I think it's maybe come true. Okay. The next, if we release some carbon dioxide from heating, we will see their heating temperature no more than 100 Celsius degree. Because if we over than 120 Celsius degree, it means maybe water will be changed to some steam. They will very large energy consumption. So we no more than 100 degree, we can release the carbon dioxide. So it is a very energy saving process. So maybe we use this process to control our power plant. and we test the power plant performance. We can see the in the right side, we use our power plant to capture the fuel cell gas, maybe 12 to 20%. And we can find their capture efficiency will approach to 90%. And we also to develop some new dispersion tool for low carbon dioxide concentration battery. Because some battery, their carbon dioxide concentration not too high. So when we use our novel absorbent to work this battery, we must redesign our process. We can see in typical disperser, their bubble will be large. So their efficiency is very low. If we use our new dispersion tool, their bubble will be very small. This means the interface between gas and the liquid is very large. So their capture efficiency will be approached to 19-17%. It's high efficiency. This novel absorbent is not is our develop our team. So this is a new one. I think maybe it's it can cooperate some company to construct more big carbon capture system. Thank you.
I have a question to the Ding Wang, because you mentioned your pilot plant is about 20 tons
Yes.
per year of
Yes.
CO2. I'm wondering, such is kind of the successful experience. Can you 1,000 times bigger to
yes,
capture more?
This is a good question. This must be engineering join this group.
Okay.
I'm sorry, I'm academic people.
It's just a chemical engineering point of view.
Yeah.
But you should need another people's support
Yes.
to
yes.
commercialize.
Yes,
To
yes.
get more.
Yes, yes.
100 times. No. I mean 1,000 times of 20 tons of CO2 is possible.
I think maybe because it must take some data to
Yeah.
simulate by
Yeah.
computer.
Okay.
Okay.
Wonderful.
We welcome if somebody they have expert for engineer design.
Yeah.
You can contact us.
Okay.
Okay.
Wonderful. Yeah. Dr. Jen, please.
Okay, what I'm going to share with you is our in-methane business model. So actually, we have been through many technical lessons over the last 45 minutes. And here I would like to use this slide to explain to you that how to conclude what will happen. So remember that we said at the beginning, we are utilizing CO2 which has been emitted from these large CO2 emitters, carbon dioxide emitters, in their chimney, in their flue gases. So where would be these kind of industry, like a steel and iron, like a cement, like aluminium, like a fertilizer, pulp and paper, petrochemical, textile, and very important is the power generation as a fossil fuel base. We are not talking about renewable power generation. We are talking about fossil fuel power based power generators. Well, how we call these type of manufacturer? They are really large CO2 emitters. They emit lots of the CO2 through their chimney to the atmosphere, which are contributing to the very high volume of greenhouse gas emissions, and that tackling the climate change. So what we're going to do is we are going to capture the CO2 in their chimney from this very hard to abate industry. And so we use the CO2. Normally it would be a greenhouse gas released to the atmosphere, but we capture them, use them as a raw material. Again, so these will be a carbon credit created here. And then what we're going to do is we capture them. But as we say that we divide these in two sides. So we have a domestic country that they have a lots of emitters, and then they emit CO2 here in the domestic side. Like in Taiwan, we do have the different type of large emitters, CO2 emitters here. But we're going to do here that we are going to, we need to have H2, let's say green hydrogens. But in Taiwan, we don't have enough renewable sources to produce a green hydrogen. If we don't have a renewable sources to produce a green hydrogen, then it will be brown hydrogen. Brown hydrogen, it creates lots of emission again. So it will be carbon leakage in our process for hold the pattern of a carbon credit. So what we're going to do is that we don't have a very green hydrogen here. Then we would like to capture, as we said that earlier, to capture of the CO2 to liquidize them and to transport them or to ship them is much easier than hydrogen. So we're going to capture the CO2 and liquidize them and ship them away to where the green hydrogen can be realized much easier or less complicated or less with less prices and more economic. So we ship the CO2 away by the boat of the CO2 shipped carriers. And then, so go to overseas. For example, we're looking for the to produce. There will be a production site to produce methane, or to produce ethane and propylene, and the propane. Sorry, and where you see with these kind of overseas to find out why we choose this site, because they have better sources of green hydrogen can be produced. So for example, they have a better renewable energy of solar, wind farm, and also as well as small scale of hydro, for example. So we found many places like this in the world. Remember at the beginning with Irina told us where are the H2 can be exporting from South America and from Africa, from from Australia, for example, like that. So if we're shipping our CO2 capture to the places that with a lot of renewable energy sources that can produce hydrogen. And also, we also found out that in this area, that could produce also the biogas emitters, for example, at this one. So not only the renewable energy can produce a green hydrogen, but we also have a two-grade hydrogen from biogas emitters. So who will be the biogas emitters? For example, like a wastewater treatment plant. As mentioned earlier, our American guest here that just mentioned that from agricultural sources, the biogas emitters also from landfill side, because the landfill side, they also release lots of methane, and also from food and beverage industry, from animal and livestock farming, for example. So there are two different emitters or two different type of industry we are cooperating with our business model. One is the CO2 emitters from the manufacturing industry, which are hard to abate industry. And also the other part is more for biogas emitters. So CO2 emitters, they to capture the CO2, but the biogas emitters is to, we use our technology, we have a patent technology, so we can we can produce actually with the H2 or hydrogen and also carbon monoxide in this case. So what we're going to do to make it simpler, if we are in a country, we capture the CO2 from the CO2 emitters, and we found out in our country that we have enough sources of renewable energy H2 for producing hydrogen, green hydrogen. Of course, we can do it domestically. For the reactions. If we found out in the country, like in Taiwan, we can capture the CO2s from the emitters, but we don't have enough sufficient of a green renewable energy to produce green hydrogen. Then what we're going to do, we ship them away. Okay, let's say that if we are the country, we have enough sources for hydrogen and carbon monoxide biogas emitters. We're going to do it. There will be a whole system, whole business model happening here. So the production size of the e-methane and e-propane and e-ethane, what they're going to do is they produce all these gas. So there are two very important gases here. One, CO2 to produce e-methane. That's what we call CO2 used to be a greenhouse gas. Then now we use the CO2 to meet green hydrogen to produce very important sources of E-ethane, or we say E-alkyne, these kind of C1, C2, C3 gases, which are important, then they can be utilized back to the industry for as a combustion. For example, the industry can use the C1, C2, C3 for combustion, for residential heating, also for power generation. Again, what happening for a gas company? For example, before we are going to phase out of fossil fuel, but now what we're going to do is that we're replacing methane. The LNG is here. Normally, these are the gases, natural gases we are digging from the fossil fuel. But now we recycling them, reproduce them from where the CO2 was emitted to the industry as a raw material. So it's very important, the cycle here, that we have ethane back to the industry. Back to the industry, we can use for heating. We can use for combustion again. So they don't need to dig the fossil fuel from the ground. And then this is something when we phase out of a fossil fuel, then there will be a closer loop of the cycling. Also with E-ethane and E-propane, as mentioned by Ding Wang, they are also very important raw material for the chemical reactions and chemical industry, which, because actually they are environmental friendly, we say zero carbon neutral, or we say carbon negative methane, and also the gases here. So what we're going to do is when you go back to the chemical reaction industry, and they will create a net zero chemicals. So this is what we mentioned in the next steps. Okay, so how we mention about this, if in the country, we have sufficient sources of renewable energy, sufficient sources of biogas emitters to produce green hydrogen and also carbon monoxide. Then to produce methane, ethane, and propane, we say alkyne. And so we have different choices here. Go back to the industry for as a resources for combustion, and we can send a it can have a different business type. It go to the next chemical reactions for producing net zero chemicals, or for Taiwan, for example, we send away the CO2 capture to the other country to produce methane. But in Taiwan, we do need gases too for our future life. So what can be happen when they be liquidized again? Then they can shift it back as a gas, natural gas, but it's a synthetic, is a thing, and it's synthetic gas is a natural gas back to be used for our future, for example, for the industry or for our life in the future. So what is happening here is easy to say that in our e-methane business model, we are using, or we are looking at all the business model is on a global basis to achieving net zero goals and to optimize our carbon credit values by using the global resources. So a domestic without sufficient of renewable for producing green hydrogen, then we shift them away. But in the places where we have enough resources to produce green hydrogen and carbon monoxide, then it will be a whole system coming back here. And with when we have a sufficient of e-methane produced here, it go back to the industry. It go back to the industry for produce different chemicals and for the future reaction. And also they can be shipped back to the country. They really need natural gases. So what we're going to do in this way, and we in National Cheng Kung University in our team, we have many research, and we also have a pilot plan already done in Taiwan. And we are requesting for international partners and investors. Who will be the partners for us? We are requesting for partners who are CO2 emitters. The industry emitting lots of CO2 in their flue gases. As we say, that the industry like a steel iron, like a cement, aluminum, fertilizer, pulp and paper, and petrochemical, textile, and for example, etc. So one of our partner, we are calling for future participation or with a cooperation. If you are CO2 emitters in your chimney and you found it's hard to reduce to capture or to reduce your greenhouse gas emissions in your company as emitters here. So these are the partners that we're looking for. The second emitters we are looking for as a partner is biogas emitters. As we mentioned earlier, that these emitters that emit CO2, so CO2 will be captured, but these emitters, they release the emission as like a biogas. So what kind of industry? Wastewater treatment plant, landfill sites, food and beverage, agriculture, animal and livestock farming. So there are two different type of emitters or two different type of industrial partners we are looking for. And also these are more biogas partners, producer emitters we are looking for. So these are the partners we're looking for. The third partners we are looking for is if you are the size can produce renewable energy, which are really needed for producing our hydrogen. For example, so it's a place like a solar plant, wind farm, and also small scale hydro. Actually, we found out just in, I think it's mid of October, the largest solar farm was connected in operation in Abu Dhabi, in UAE, not long time ago. So it was the installation of the solar plant, I think was the largest so far in the world with 2.1 gigawatts of installations. And actually this is a place with that can generate of a sufficient of a renewable energy. That is really cool for us. So if we have a partner here, for example, in the country like here with sufficient energy. So these are the partner emitters. Renewable energy sources with the sufficient one. The third one will be the biogas emitters. So these are the image we say is a partner for us. The fourth partner we are looking for is actually the shipping company. It's the, we say is the CO2 carrier. Back to here, it's not CO2, it's a LNG. It's a natural gas, but it's a natural gas, a synthetic natural gas. So there were two carriers companies. So one, CO2 emitters industry. Second is biogas emitters industry. Third is a renewable industry. A fourth one, we are looking for a partner here is actually a shipping company with these carriers that can be used on. And in the future, so for most important, these are the separate sources, but we also need a partner. Very important is who is going to produce to make a realization of this CO2 plus hydrogen equivalent to methane. So we need to have a really important partner who would like to have the space, land, and also the finance, okay, financial background. So production side will be our main future partner, which is to realize our business model in the real cases. And it can be happened in overseas, in any places. I spoke to many clients. For example, they are in Scotland, or maybe they are in like in Germany, like in France or the other country, who has a big traditional, we say, big industry with chimney release CO2, but also they have a sufficient renewable sources. They also have a sort of, well, you know, the biogas wastewater treatment plant, it comes from human resources, it can be from industrial resources. So when we have these places that then, so we are ready for cooperating with these kind of country, and that to choose a right place for the production site to produce the methane, to fulfill the full cycle of this business model. One thing I would like to add on with this one is carbon credit. So where the carbon credit, it will be additional value into this business model. When we cut off the CO2 emissions here, so there will be a greenhouse gas emission reduction credit from here. So because in our cases, we produce hydrogen with zero, or we say green hydrogen. So there will be no carbon leakage. But if we are shipping out the CO2 into the production site overseas, of course, there will be a leakage for this transportation here, but we try to reduce them and to control them. And so in that case, but in this case, in our business model, the carbon, or we say greenhouse gas emission, it will be registered, it will be issued as a valuable or creditable, or we say tradable sources to add value onto this whole process. And so this is the case. The third case, where are the economic, or we say, where are the profit it can be coming from, because with the e-methane we produced here, it's really creating the full cycle of whole industry. So the valuable, because actually as Professor Wang mentioned earlier, when the e-ethane and e-propane, they are producing more than the shale gases, for example, then there will be more valuable process that can be created and go back to the net zero chemical for the future. So these will add on a lot of the valuable sources to these financial. I mean, financially, it will add on a lot of value here, and also going back to here. So it will be cool. And so in that case, we're saying that for the investor, so we're talking about what type of partners we are looking for: CO2 emitters. We are looking for biogas emitters. We are talking about renewable industry and also the production side to be realized the case, and the ship companies. But one thing that we are also ready for calling for investors. Actually, National Cheng Kung University already has some test or pilot plan already done, and that we are ready to show to our partners and investors. Investor means that we need to have also finance-based investment that will be done. So I would like to share with you what we are, where we are now, and then how can we demonstrate to you. For example, as we mentioned earlier, that National Cheng Kung University has one site, one pilot program within the academic, we say within the academic sites, but we have also been realized with a tested into Formosa petrochemical companies to help them for targeting to net zero emissions. So our pilot demo site is a small scale, has been realized, and then it's trying to enlarge it. I remember that Dr. Peng mentioned earlier that so if you have a 20 tons production, we like to enlarge it to 1,000 times. This is really the case that we needed. This is the engineering that we needed to be realized into the real site, but this is just a small testing site. Then after this, all the engineering work has been tested, then we can enlarge it to another 1,000 times, 100 times, 1,000 times. So this is one of the testing, engineering testing has been concluded already. Then we are ready for showing to our investors and also partners how these projects can be realized. Second thing is that we would like to thanks to the enterprise that contributing to our research and the pilot programs. Actually, you can see all from these research and pilot programs where they're from. They are large emitters. And these are the large emitters that produce, we say, emitted CO2 from their flue gases chimney that we can be used in the future. So thanks to them for contributing to our research. I would like to add one more thing. I forgot to say that earlier. When the CO2 is captured, very important is contributing to what is important. If the large emitters, they are power generation companies, like in Taiwan, like Taipower, if their chimney, all the CO2 from their flue gases has been captured, it means it will reduce a lot of the emission factors from the power grid. And what will be happening, and it's really, I think it's enormous financial additional value add on for whole the industry, using electricity. As we know that in Taiwan and as well as many other countries, that if a company, they are doing like a greenhouse gas inventory, and they found out there are two types of greenhouse gas emissions can be accounted. The first one we say is called Scope 1. Scope 1 means the greenhouse gas emission emitted directly within your site from combustion sources, from we say the textile sites, and also from the process, production process, or their then use. But the second type is called Scope 2. Scope 2 of the greenhouse gas emissions are coming from the utilization of their energy, especially electricity or steam, that are generated by the other sources. If these electricity are generated by fossil fuel-based power generations, it means that the greenhouse gas emission from utilization of the Scope 2 will be much higher. And to the statistics in Taiwan, most of the industry, when they are accounting for Scope 1 and Scope 2 emission into together, we found out the Scope 2, it means the use of electricity is accounting for more than between 60% to 95% of the total emission, or we say total greenhouse gases generated through Scope 1 and Scope 2. So what does it mean? Accompanying most of their greenhouse gases are from utilization of electricity. And if our business model is cutting off the greenhouse gas for these fossil fuel-based generation company, it will add a lot of value. So it means our emission factor of the power grid will be efficiently or dramatically decreased or reduced. And this is not only helping for the company associated from emitters, renewable energy, biogas, or the shipping company, or the production side. The cutting emission factors is really, really dramatically, or we say will be largely and most enormously helping the whole industry. What I mean the whole industry, it means thank you. The whole industry, it can be like such as important industry, semiconductor industry, and always say electronic industry in Taiwan. You know, as we said earlier, when their greenhouse gas on 60% to between 60% to 95% produced by using of electricity. So our business model helping cutting the emission factor from the industry, for example, maybe by 40% or 50%, is really helping the major industry to reduce their greenhouse gas dramatically. So we say here, our in-methane business model has double value. One is to finance or to fruity the industry, emitters, and all the associated with this loop. But the second one, which is more important and make me very, very exciting to join Professor Chen's team in National Cheng Kung University for these cases. Really exciting that I would like to help for the countries like I am in Taiwan and also the other country. When you have electricity or you have the large emitter and we so-called hard to abate sectors, then we capture the CO2, reduce the greenhouse gas with carbon credit. And also, not only the carbon credit we generated here, we also produce different type of a new financially add value process or with a product in the future. And dramatically, we're helping the industry, I mean, the whole industry other than us, to reduce their greenhouse gas from use of electricity. This is really important for the competition and to reduce also we say carbon tax for future. So this is something very important, and then we feel very exciting to share with you that our business model can really helping to achieving the net zero goal, and also to have a values of carbon credit by using global sources. So we are not stucking us thinking about the way to create our hydrogen green in the local places. We could have renewable sources, but we can use global basis as a whole to produce, to think about. So we enlarge our view to see this is really a cool world that we're going to do. And we thanks to all these companies participating in our program. Now I would like to share with you that actually this project is led by Professor Chen, who is a distinguished professor of National Chenko University in Department of Chemical Engineering. And also he's also the coordinator, a very important person for Circular Economic and Green Energy Group Office of Science and Technology for Taiwan Executive Yuan. So he's also very important technology review committee of the National Development Fund that will be Executive Yuan of Taiwan. And then in this case, I would like to share with you that if you'd like to contact us, then we have a contact us email in National Chenko University here. And then we'd like to share with you that in the future, that what we're going to do with our team is that we also have a professor, we have a Paul Huang. Paul Huang actually was an ex-general manager of a Monsanto company in Taiwan. He's really experienced chemical expertise. That he was also a CEO of a Formerty Enterprise and also a managing director of Asia Pacific Sales L Group. We have also Professor Wang, as we mentioned here, that he's a dean of the engineering college at Southern Taiwan University of Science and Technology, and also a professor of Department of Chemical Engineering, Material Engineering. Another is a coordinator, Ken Lai. And I would like to also mention that actually who is doing all the difficult job for us for this presentation and also this assistant for these cases is Ri Chen. Mr. Ri Chen is actually a deputy chief of a technology transfer center for National Chenko University, manager of the non-E international intellectual property offices and general manager of the dynamic internet. Myself, then I would like to put you here that I have more experience rather than in carbon credit before. That's why I'm really excited to share with you that actually to share with you how to reduce the carbon emission of CO2 from the chimney as a greenhouse gas to reproduce them back to as a natural gas. And then to utilize them as a circular economy in the future, to reduce also the emission factor from the power grid is also a great potential possibility in our case. We're helping the industry to reduce their cost of greenhouse gas emission reduction in the future. These, I think, is normal, that it's unaccountable at this moment, and it will be a great help for future. So,
okay, thank you.
The floor back to share with you that this is Professor Chen, and also this is the power plant in National Chenko University. These are the graduate.
It's Dr. Chen's team. Huge,
Yes.
such a huge team. Okay.
And there are many people has been contribute to this one, so we'd like to thank them at this one at once. And Professor Chen, the floor is on you. It's yours.
No. Before the Professor Chen, I will ask you questions because you are how many times a COP? I'm wondering, by using the NCKUs, such as kind of product, you are in COP. What's the importance? Why you want to do that in COP 28?
I feel that actually I've been participating in COP from 1997.
Yeah.
So when the Kyoto Protocol was signed at the time, and I work in DNV as a certification company. So as it's more like a carbon credit certification auditor. Then a participating COP with another head is from the trading company for carbon credit. And now this is the most exciting COP that I'm joining, because what I feel very important is I'm helping the industry, not only for the projects, but also for the whole industry that we can utilize. And then actually is really economic.
Okay, I will send the questions to Ding Wang. It's your first COP, right?
Yes.
What's the importance of COP for chemical engineering? For the
Because next year is fossil fuel phase out, and our research team proposed some resource method to support e-alkane, including e-methane, e-ethane, and e-propane. If we can transfer into ethylene or propylene, we can support some raw material of the chemical industry. So I think,
Okay.
yeah.
Yeah, thank you. I would like to give the floor to Dr. Chen Zhiyong, and probably Doris, maybe you can have translations. Okay, Dr. Chen Zhiyong, please.
Speak louder.
Please change your screen directly to Dr. Chen.
Can you
please.
unmute it? Can you unmute your screen?
Yeah, please go.
Professor Chen, the floor is yours.
OK，首先感谢彭秘书长的今天的帮忙协助了主持，让整个会议进行相当的顺利了那这个计划，说实在，我们要来感谢的几个单位啦。第一个教育部因为教育部在成大，我们知道近零排碳这一个议题是很大，需要很多人才，培育人才所以教育部呢规划了一个计划，在成大来执行。目前在台湾唯一的一个培训中心所以这个东西我们在成大呢建置一个人才培育的基地那至于
陈老师，我先帮您翻译，然后等一下再继续好吗？
没有，你等一下我讲完，因为时间快完了那第二个呢，我们要感谢的以前的科技部，现在是国科会它有一个架杠计划因为它补助我们要成立，把学校的研究呢，把它适度的释放出来成立一家公司所以我们干了一个 power plant 就刚刚报告你们安南区报告的那个 power plant， 那是有科技部国科会那边来补助的。那当然这计划执行过程里面也承蒙了经济部、还有环境部、还有化工所的帮忙当然在这个里面呢，我想一个首先真的要特别感谢的，我们赖副总统莅临这个基地来启动仪式让我们在整个台湾曝光出来，征集到相当的资源那总而言之要感谢的人相当的多我想不一一来报告以上呢，感谢大家的参与与聆听，谢谢大家。
Okay, thanks, Professor Chen. I will try to explain a little bit, to translate a little bit what Professor Chen has been shared with us. Actually, he would like to thanks to all the supporters and with us financially, and we say the real work that has been done, including the Minister of Economics in Taiwan, Economic Affairs in Taiwan, with also okay, so we have a minister, we say from the Minister of MOEA in Taiwan here, which is from Sustainable Development, is that?
Yeah.
Yeah, okay.
IDA, I'm from
Okay.
IDA. In that development administration.
Oh, okay,
Under
great
Ministry of
job.
Economic Affairs.
Okay,
I'm Dong Chen.
okay.
Professor Chen,
Professor Chen?
you fine.
Okay. Yeah. Okay. Would you like to have some word
Oh,
contributing to us?
I have visited this site
Okay.
sometimes. Yeah.
Thanks very much. Okay, thanks. Because I would like to continue the thanks that Professor Chen made to the other department. It's like the Science and Technology Council that in Taiwan, and also is Minister of Education in Taiwan, because contribute lots of financial and support here.
Let us finish.
Sorry. Okay, so Professor Chen also mentioned that actually the Vice President of Vice President Lai is really supporting to the research and also to the realization work for this our pilot program too. And he also attended as in the kickoff meeting of our pilot program in Thailand in Chengkong University. So he would like to thanks to all the officers and also the distinguished guests that who contributing to the to supporting the project itself. And then Professor Chen, anything else? 陈老师，您还有什么事情想特别再跟我们继续再说明吗？
那个感谢今天王博士啦，还有简博士，还有周在的，我们真的要很感谢彭秘书长很用心的来规划这个案子的进行。那我想未来呢，还是要承蒙大家一起来努力。那谢谢大家。
Okay. Thank you. So one more person that we forget to thank, great thanks a lot is to Dr. Peng to actually planning for all these, or preparing for all these very nice events here in COP28. We all want to work together with you, and we are calling for international partners and investors to contact us in the future. If you have any questions, want to go to the end of the slides, we'd like to share with you that our contact person. Then we have a QR code to share with you. Then you can contact us in a faster, easier way in the digital side.
Okay, thank you. And I'm wondering, we have some friends probably from Taiwan. And do anyone have the question or comment? Yeah, want to talk? Only microphone here. Anyone? No? Okay, thank you all the guests here. And we actually, lots of people go through from the US, lots of people enjoy our talk. It's the first NCKU, National Chengkong University, have a side event here. And we thank you to Dr. Ding Wang and Dr. Jian to join us. And it's his first COP. I think next COP you will be here, right? To promote. And Dr. Jian will linkage about such a kind of project with the carbon. And I think it's very important. And also, we also need the Ministry of Economy Affairs support about this project. So let's keep going about this project in the future. Okay, thank you very much. Give applause. Thank you.